So today, first, I want to go over this. Okay, so this is the wall. We know what to do with that wall. We have brick, we have air, we have glass wool, another air layer, and then gypsum board. This is inside and this is outside. Okay, so if we have these elements and if we use the Excel file, if we start with the exterior one, okay, so this is brick. I'm starting from scratch, so I'm doing, I know you know how to do this, but anyway, I'll do it again. So we have 4 inches, so the width of the brick here, so it's 4. I'm going to delete all this just to avoid confusions. So in the external layer is brick, or the external finish, so external is brick. The thermal conductivity is not this, so we have to go to thermal conductivity, brick. I have a yellow column here. I will explain that later, and I will upload this Excel file because it's different from the one that you are working with. So brick common, so this is 3.47. 3.47. Okay, second layer, air. Air, 2 inches. So we have 2 inches, and is it 0.9? Yes, it is 0.9. So the thermal conductivity of this air layer is 0.9. The third layer, glass wool. Glass wool. 6 inches. And the thermal conductivity, 0.23. No, sorry, 6 inches here, 0.23. We have another air layer, 2 inches. The thermal conductivity is the same, 0.9. And finally, we have the gypsum board. Gypsum, inch, and the thermal conductivity of the gypsum board. Do we have gypsum here? Yeah, gypsum board, 0.98. Okay, so 1 inch gypsum, 2 inches air, 6 inches glass wool, 2 inches air, and 4 inches brick. Okay. What is the thermal resistance? 35. Is it enough to meet the passive house standards? It's not. But let's look at this in terms of vapor resistivity. Okay, so now we have to work with this, with the vapor resistivity. So what about the gypsum? So this is new. On the gypsum board, the vapor resistivity is 60. So it's this column here, vapor resistivity. So if we are talking about gypsum board, this is 60. So gypsum, the vapor resistivity is 60. We don't have anything here, by the way, this is 0. Okay, because this, in these empty cells, the width has to be 0, so that even the vapor resistivity can be 0. So gypsum is 60. What about air? The vapor resistivity of air, it's 5. 5.5. Air vapor resistivity 5. What about the glass wool? The vapor resistivity of glass wool. So we go to where is it? Gypsum. Here, glass wool, vapor resistivity 10. Well, it's 10. The air, the vapor resistivity is 5. Here, the same as this layer. And finally, we have brick. So vapor resistivity of brick, common brick, 50. Here we don't have any layers, so this can be 0. Okay, so now we look at the graphic, and we might have condensation issues. Okay, so this is the first option. Oh, by the way, I think I haven't changed the, okay, the outdoor temperature is -10. Okay, so indoor temperature 70, outdoor temperature -10. So here I have to type -10. Does it matter? It matters. It makes things even worse. Okay, now it's there are still condensation issues, but the colder the outdoor temperature, the more difficult is having this without risk of condensation. Okay, so that would be the first answer to that question. Oh, what if we have the area of walls? Okay, so the area of walls should be the area of walls 100, no, 1200. 1200 square feet. Okay, so here we have the thermal. I changed this, so when you click here, you see that it's the U value times the area of the walls times indoor minus outdoor temperature. Okay, so in this Excel file, this number here is the heat load through that wall. We have the U value, we have the area, and we have indoor minus outdoor temperature. Okay, so this, if you copy all these, if we make a picture, okay. So this is the wall without, here you go, without meeting the passive house standards. Okay, so this is a wall that it's not acceptable. It's below the passive house standards. We have condensation issues. Okay, so this is the first approach. Now we have to make it better. So to make this wall according to the passive house standards and without any condensation issues, what can we do? Okay, so we can say wall passive house. So we know that this R value should be above 50. The only way we have to do this is to increase the thermal resistance, and we have to increase the thickness of the glass wool. So instead of 6, let's try with 8, 42, let's try 10. Okay, with 10 inches of glass wool, we meet the passive house standards. So first, we have solved the passive house standard. What about the condensation? It's not solved yet. So what would I do? The rule of thumb, we need a vapor barrier inside the thermal insulation. Okay, so here I can copy these values here. So we have the gypsum, we have the air cavity, and now okay, I'll do it again. This is gypsum because I have to change all the rows. The thermal conductivity is 0.98. The thickness is 1 inch. Okay, And what about the vapor resistivity? 60. Then we have air. The thickness is 2 inches. The thermal conductivity is 0.9, and the vapor resistivity is 5. And I have to insert here the vapor barrier. Okay, so what is the thickness of a vapor barrier? It's something very thin, so we can type 0.01 inches. Okay, what is the thermal conductivity of a vapor barrier? It's not relevant. So we can type whatever you feel like, whatever. Okay, so let's 100. But it's not relevant. This value, it's not relevant in vapor barriers. But what is the vapor resistivity? So if you go to the vapor resistivity, here at the end, we have that, we have different membranes, okay? Because this is a membrane, it's something very thin and it's covering the whole wall. So we can have aluminum foil, polyethylene, this is plastic, and this is painting. The most effective is the aluminum foil, okay? And it's the vapor resistivity is above 40,000. So it's an extremely high number. So we can type here 40,000. Okay, look at the graphic when I click OK. Let's make it even bigger. Okay, this is what I want. The effect of the vapor barrier is this. So the dew temperature drops dramatically here before reaching the thermal insulation, because this layer is the thermal insulation, this line here, and we have to make the dew temperature drop before this layer. If 40, this is it's more than 40,000. It can be 50,000, it can be 100,000, or it can be 400,000. The idea of the vapor barrier is that this has to drop here. Okay, so this value, I don't know, maybe with 100, 1 to 3,000. Yeah, it's, if we make it bigger. Okay, so the value, it's not relevant. It's not that, oh, it's 200,000 or 155,000. It's not relevant. If we place a vapor barrier here, we make sure that this is the effect. So the dew temperature drops here and we don't have this condensation risk. Okay, so with this kind of envelope, we are meeting the passive house standards and we are solving these condensation issues. So we can copy all these here. There you go. Okay, and we have also reduced the heating load. Here it was 2,800 and here's 1,800. Okay, so we have reduced a lot the heat load because we have increased the thermal resistance from 33 to 51. Okay, so this envelope, this one, the passive house one, it's more reliable than this one, than the first one. Why? There are two reasons. We have a good R value. I mean, that value, it's good. I mean, 20 years ago, 33, it was more than enough. But nowadays we have to go farther. So we have to meet these passive house standards. So we have to make this in this northeast area of the United States. Yeah, 50, it's better than 33. So let's do it. And then if we are using a vapor barrier here, we avoid these condensation issues. There is a lot of controversy whether we should use vapor barriers or not. And you might find both options. There will be experts that claim that no, don't use vapor barriers because, and there's a good reason for not using vapor barriers. But there are also good reasons for using it. the reason for not using vapor barriers is that if we are not using them properly, we might have other issues with condensation, with water leaks, and yeah, if we are doing things wrong, we are assuming that we are not doing things wrong. Okay, so anyway, we have all this semester to talk about vapor barriers, air barriers, and all that stuff. But from the building physics point of view, using vapor barriers prevents condensation issues. Here we don't have any vapor barrier. We can't have these kind of issues. If we had this, we wouldn't have issues. If things are, if the company, the construction company, is good enough and the workers are experienced and they know how to handle with vapor barriers. Okay. So that's it. That would be the summary of the wall. So here we have the first proposal. We have this value, it's not enough. We have this, these two lines, the dew point is above the temperature. So when that happens, we can have condensation. How can we solve it? Increasing the thermal insulation and placing an air barrier here inside the glass wool. That's important. This is the rule of thumb. It has to be inside. If it's outside, it will be a mess. Okay, but the vapor barrier has to be inside the glass wool. Any questions? I don't know if you have done this. I've gone over all the assignments, and some of you submitted both options, this one and that one. Some of you didn't take care of the condensation. Some of you submitted only the first one, but we need to know how to turn this option into a passive house option. Okay, so we need both for walls, and we need both for roofs and floors. Okay, so what would be next? The roof. So if we go to the roof, this is the floor. Okay, so this is the roof tab. Inside, we have the gypsum board. Okay, so we have gypsum board. How many? 1 inch. So it's 0.98 and 1 inch. Then we have air. Air, it's always, it's 3 inch. Okay, so it's 0.9 thermal conductivity of air. So air, 0.9, 3 inches. And then we have the glass wool. The glass wool, it's 6 inches. And thermal conductivity, it was 0.23. Okay, glass wool, air. Then we have concrete. And it's 12 inches. It's 12 inches because this is the structural element, the concrete slab. And what is the thermal conductivity of concrete? Let's find out. 4.1. 4.1. And finally, we have asphalt. Well, asphalt, it's something that it's not, it's waterproof. So we have to protect the, especially if this is a, usually this would be a flat roof. So we need to protect this flat roof against rain. So asphalt, it's something that can be considered as a waterproof material. So let's make it asphalt. We don't have any plywood here, so that would be 0. And the width is 1 inch. It's too much. And what is the thermal conductivity? Asphalt 433. Okay, and now we have to deal with the vapor resistivity. So if we start with the asphalt vapor resistivity, it has to be 100. Okay, so this is the vapor resistivity. So let's type here 100. This can be 0. What about the concrete? Concrete, it's 50. So the vapor resistivity is 50. What about the glass wool? We did it before. Glass wool is 10. So the vapor resistivity is 10. The air, I think it was 5. Yep. 5. And the gypsum board, did we? Yeah, it was 60. Okay, 60. Okay. Well, again, it's not a good solution because the R value it's 34, and we do have condensation issues. What do we have to do? Look at this. It has to be 80 because if we are talking about roofs, the recommendation for the passive house standard is 80. We only have 6 inches of, let's say, 18 inches. Okay, with 18 inches is 86. With 16, it's 77. Say 17 inches, 82. Okay, so we need 17 inches. Look at this roof. Okay, so if we want to meet the passive house standards, we have 12 inches for a concrete, a foot of a concrete structural element, and then 17 inches. So we are talking about almost 3 feet. Okay, so the width of this roof, it's around 3 feet. So get used to it. So I'm when I attend design presentations and you show or you display your sections, usually the section of the section of the roof is just a line. Well, it shouldn't be a line. It's a 3-foot layer, especially if you are working with flat roofs. If you are working with tilted roofs, it's better because you can embed the structure within the thermal insulation. But if you are designing flat roofs, make sure that you have 2 to 3 feet the thickness of that roof, because otherwise it's impossible having this kind of R value. Okay. Okay, we're done with the passive house, but we are not done with the this requirement. So what do we need? We need another. Does it work if I insert here? Yeah, it works. Okay. You can always click here, and if you right click, insert, you have a new layer. Okay, so we have a new layer inside between the air layer and the glass wool. So it's inside the thermal insulation. So this is the vapor barrier. And we can have the same values here, 100.01 and a huge value here. .01, and let's say 200,000 or whatever. Oh, and now we have to, because we have inserted the line, but we have to make this, okay, and this is 200. No, it doesn't work. Okay, so do not insert another layer here because yeah, if you want more layers, I think I have to change the layout of this. So let's let's move all these values down. We have the vapor barrier here. So that would be 4.33, 4.1, and 0.23. That will be 100. The thickness, the asphalt was 1, the concrete was 12, the glass wool was 17. The thickness of this is 0.01. Okay, and then the vapor resistivity, the asphalt is 100. This is 50. This is 10. And the vapor barrier is 200,000. There you go. Okay, so you see that even using here 200,000 vapor barrier, we might have issues. What if we make it bigger, 400? Okay, so that would be complicated. But we need to understand that this roof can have some trouble with this. Why? Because the asphalt is, look at this, we have a drop of this element because the asphalt has a high vapor resistivity. If this value were lower, we would have less issues here. Okay, so this is because we have something impermeable with a very low permeability outside the house. And this is always something that we have to prevent from happening. So maybe there are better waterproof layers than asphalt. Anyway, you see that here we might have issues. This is not, it doesn't mean that, okay, you have to rely on that. It's just to make sure that, okay, if we do this, most likely we won't have any issues. But here, roofs are complicated because when it comes to roofs, we can, yeah, all the heat tends to go up and we are exposed to rainwater. So roofs, especially flat roofs, are always, so this is a warning. Okay, so if these lines, even with a vapor barrier, it's too close, these two lines are too close, we have to pay attention to this point. Okay, so this is just a warning. It doesn't mean that we will get or we won't get this interstitial condensation. We have to be careful with this, and probably we need to ask experienced people in the area. Okay, so what have you done to, what is the detail for that roof? And in your 20-year experience, what do you recommend me? And then you have to talk to people that have been working on this specific site or this specific place for a lot of time to prevent these issues. So these are warnings. If these two lines are not too close, okay, that's fine, it will work. But even if we are using vapor barriers, and even though the lines are close to each other, we will have issues. Okay, so that would be now we need the area of the roof. So the area of the roof is 1560. Okay, and this is the thermal load. So we copy this. There you go. This is the second option. I haven't copied the first option, so that's up to you. Okay, and finally, you have to do the same with the floor. Okay, the floor is easier because we have only 3 layers: concrete, glass wool, hardwood. And again, you have to do the same here on the floor chart. If we can have condensation, then we have to place the vapor barrier again close to or in the inner side of the thermal insulation. Any questions about this?
No.
Okay. go over what you have done. And well, here you have the solution to the walls, the original option, and the and the passive house option. Here you have a solution to the roof with the passive house option. You need to paste here the first option, and then we need the floor. And when it comes to floors, I want to explain you something, because now we are going to move to Revit. And well, I will. So this is, let's make it bigger. And there you go. Okay, so this is the house, the building, whatever. So we have the walls, two walls, and the roof here. And this is the soil. So when it comes to floors, there are different options. We can have a floor and we don't have any crawl space, or we don't have any air layer or air chamber or air cavity underneath the building. So the floor slab is resting directly on the soil. Is this acceptable? It is. I don't recommend you do this. I think it's always good having an air layer between the soil itself and the building. But there are thousands of buildings like this, that we have a floor slab directly on the soil. So now we are going to place numbers. Okay, so the indoor temperature is always 70 Fahrenheit. Outdoor temperature is, in this example, it was -10 Fahrenheit. Okay. And okay, so when we are analyzing this, when we are analyzing what the heat does, so we know that a lot of heat is going through the roof. Why? Because the heat tends to go up. Okay, so we are losing a lot of heat through the roof. We are losing heat through the walls. But probably less than through the roof, because yeah, so the heat tends to go up, and we are losing heat through the wall as well. And finally, we are losing heat through the floor. But as the heat tends to go up, the heat loss that we have through the floor is not as much as the heat loss that I have through the roof. So that's why the requirement for thermal insulation for floors, it was 30 in passive house standards. We have R50. R50 for walls, 80 for roofs, 30 for floors. Okay, so that was the idea. And most of the floors that you will find, they are uninsulated, so they don't have any thermal insulation. And there's a reason for that, because if we have heat here in this point, so most of the heat will go either up or through the walls. That's fine. So if this heat tries to escape through the floor, it has to go from the indoor to the outdoor. The outdoor temperature here is also a -10. Okay, so the heat has to go all this way. So it has to go through the soil, and then it will go up again, and it will find the -10 Fahrenheit. But this is very unlikely. Okay, so that's why heat tends to escape through, if we are talking about floors, the most dangerous point when it comes to floor is this floor to wall transition. Okay, so this is a weakness point. Why? Because the outdoor air is here. Okay, so it's likely that the heat goes that way. It's very unlikely that the heat goes all this way. So that's why the recommendation is that you have to insulate only this corner. So you have to place thermal insulation only on that corner. And you will find a lot of lectures or a lot of experts. No, you have to place thermal insulation only at this angle, at this transition between floor and wall. That makes sense because most of the heat will go through this way. But I don't recommend you do this. So if you have to place thermal insulation, just continue all this and then make sure, yes, so you can have extra thermal insulation here at the angle. Okay, but do not save money on thermal insulation. It doesn't make any sense. Thermal insulation, it's very cheap. Well, it's cheap if you have thousands or millions of square feet. It makes yeah. So but but the price per square foot of the thermal insulation, probably it's the lowest price of all the elements that we have in a wall or in a roof or in the floor. Okay, so the flooring, if you are using a nice floor with the oak or maple or whatever, a beautiful wood floor, or if you use marble or even ceramic tiles, are much more expensive than thermal insulation. And when it comes to saving money, thermal insulation is much more important than the flooring itself. The flooring is beautiful. You see the flooring every day. You don't see the thermal insulation, and that's something understandable. So you need to spend money on something beautiful, on something reliable, because you are stepping on that floor every day. But you don't see the thermal insulation underneath that flooring, and it saves a lot of money over the operation of the building. Okay, so do not save money in thermal insulation. Just uh, uh, if you place thermal insulation on the slab, it will be much better than placing thermal insulation only in that corner. Yeah, maybe it's a little bit more expensive, but it's worth it. It's worth doing this. Okay, but this is the explanation about how heat tries to escape from this building. Most of the heat will go through the roof, so that's why we have to increase this thermal resistance. A considerable part of the heat will go through the wall. Okay, so that's why this is the second highest thermal resistance. And then there will be some heat escaping through the floor, more in the perimeter of the roof in this corner than in this point. So yeah, you can place extra insulation at these points, but do not underestimate the importance of the thermal insulation on the roof, on the floor. Sorry. Okay. Now there are other. So this is a floor of a building that it's just here. What if we have okay? What if we have a crawl space? Okay, I always recommend my students or my clients do this because having this crawl space, it's a 3-foot air cavity. It saves, well, it prevents a lot of problems with moisture, okay? Because we have soil here. We don't know what's going on in this soil. So maybe there are floods. So even if we have floods, if we have a lot of water here, having that crawl space, yeah, prevents that water to get into the first floor of the building. What happens with this crawl space? It has to be ventilated, because if it's not ventilated, well, there will be life growing here, and not wonderful creatures that you can be proud of, filthy creatures. Okay, so if we don't want this, just ventilate. Okay, ventilate this. I'll use another color. There you go. Okay, so if you have this crawl space, make sure that you ventilate it. What's the difference between this detail and that detail? Obviously, this air cavity we have here. Well, in terms of energy efficiency, if we have the same amount of thermal insulation, because we always have thermal insulation, we assume that we have thermal insulation in both cases, the same amount. This is probably more efficient. Why? Because we have the soil here. So the heat going through that soil, it's more difficult, especially because of the temperature of the soil. If we have the outdoor temperature, this is outdoor temperature, is negative 10 Fahrenheit. The soil temperature, it's not going to be negative 10 Fahrenheit. It would be an average between 70 and negative 10, let's say 30. Okay, so the temperature of the soil here would be 30 Fahrenheit. So if we move from 70 to 30, yeah, so there's less heat going down than if we have, this is the outdoor temperature. If the temperature of this crawl space is, if it's ventilated, this can be negative 10 as well. Okay, because we are moving, the outdoor air is entering this cavity, and depending on the amount of this ventilation, this temperature can be the same. So the worst case scenario would be that this temperature, the temperature of the crawl space, would be the same as the temperature of the outdoor air. Okay, so in terms of energy losses or heat losses, this is worse. So that's why placing thermal insulation here, it's more important than placing thermal insulation here, because we have a lot of material, a lot of soil from this inside until the outside. Here, if we assume that the temperature of this crawl space is the same as the temperature outdoors, we probably would need more thermal insulation on that floor. Okay. So again, what is the best solution? I think this is the best because we don't have issues with water, underground water that we can have here. We have always this space, so the water doesn't go up through this crawl space. Here, the water can go up through capillarity, and we can end up having water here. So I always recommend this. But in terms of energy efficiency, and we are talking about energy efficiency here, probably this is better than this. Okay. Anyway, both options should be correct if the construction company is a good one. Okay, if you are dealing with a construction company and they are experts on doing this and they have done this in thousands of buildings and they haven't had any issues, okay, you can rely on them. If you don't know the construction company, I would go for this detail because in my opinion is better. But again, it depends. Here, probably you need to place more thermal insulation than here. And this is more expensive because you need a structural element here, and you don't need any structural element there because it's you have soil underneath this. So here you need structure because this is not leaning on anything. Well, it's leaning on these walls or in that structure, but it's not leaning on the soil directly. Okay, so be careful with floors. And why am I talking about the floors? Okay, so let's open. Okay, so we have this. We have calculated this the heating loads through the walls and through the roof. Okay, we are meeting the passive house standards. Here we have 82, and here we have 51. So now we are going to open Revit. So we are opening Revit, and we are going to calculate heating loads in Revit. So we are going to model a box today, a box with 4 walls and the roof and the floor. That's it. And then we will try to change the materials of the walls. I think you know how to do that. If you have taken CAD2, you should know how to do that, how to change the layers of a wall or a roof. Anyway, if you don't know it, I will explain how to do it. It's quite easy. But if you look at the canvas, I have uploaded a Revit family here. Okay, so I want you to work with this family because again, if you are taking CAD2, CAD3, or visual representation, advanced visual representation with me, I told you that I'm going to upload Revit templates so that you don't have issues uploading families or whatever. So I'm uploading a template, and all of you will be using the same template. Okay, so you have this on Canvas. So when you open this, remember that you have to open a new project, but you have to upload the template. So you have to browse. Well, you have to browse on your computer. I know where my family is in my laptop. Course, screen 360, Revit templates. Okay, so open this template as a new project. There you go. Okay, so I have inserted these grid lines, and well, I have inserted a few things that you need to. So here you don't have to open a mechanical discipline or whatever. So working with the architectural, it's fine. Okay. What are we going to do? We are going to work with Revit. So we are going to model this rectangle. Okay, so imagine that this is our building from grid 1, 2, 3, 4, and 5. Okay, 1, 2, 3, 4, 5, A, B, C, D. So we have these grid lines. It's just to the distance between those grid lines. I think it was okay, 15 feet. That's fine. And we are going to work with a wall, so we can just open the architectural wall. And I don't know, I have been working with different walls here. If you open the Revit file, you will have a generic 12 wall. Okay, but this generic 12, if we edit type and we edit the structure, it doesn't have any layers. Well, it has a layer, 1 foot, and that's it, but we don't have any materials. Yeah, we have layers, a layer, but we don't have any materials. So we are going to work with this wall here. This wall, the wall that meets the passive house standards. Okay, so this one with the R value of 51. So there's a gypsum, air, vapor, glass wool, air, and brick. So I'm going to put this here. Where is the Revit? Oh, it's cancel. Cancel. There you go. So I want both. Okay, so we are going to model this, or we're going to change this one. So first we have to edit type. So if we edit type, first we have to duplicate. Okay, we have to duplicate because otherwise we will change the properties of this generic 12, and we need different walls because we might have different walls in our project. And again, naming things is the most difficult thing on earth. So let's use Arch 360, and this is R. Okay, so this is the wall that we are using in this course, and the most important thing is that the R value it's above 80. Okay, so we cannot use this symbol R80. And now we can edit the structure. Okay, so we have to change the layers of this from the exterior side. Okay, so now exterior side is here, and interior side is here. Okay, so we have to do. So how many layers do we have? We have 1, 2. The vapor barrier is not relevant. Okay, so we're not going to use a vapor barrier in Revit. So we have 1, 2, 3, 4, 5. So this is the first layer. So let's insert 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay. So now we have to start from the exterior side. So the first one is brick. Okay, so you see that here we have different functions. We have structure, substrate, I don't know what this is, a thermal or air layer, finish, and membrane. Okay, so if we are placing, okay, let's do this. So let's insert the 6th one. And the vapor barrier will be this membrane. Okay, from the exterior side, what is the first material? Is brick. Brick, it's an structural material. I mean, air is not structural, glass wool is not, a vapor barrier is not, air and gypsum are not structural elements. So what is a structural element here? What is the element that bears loads? The brick. Okay, so we can keep this as structure. By category, it's brick, so we can type here brick, and we have brick common, brick whatever, brick. Okay, and what is the thickness? 4 inches. So we can type here 4 inches. So second material, air. So this is not a structure, so we have to go to thermal air layer. So this is the function. What is the material? We have to type here air, and by default we have air. So click OK. And what is the thickness? 2. Next, we have a glass wool. So it's a thermal insulation. So it's another thermal layer. What is the material? Do we have glass wool? We don't. So what do we do? Do we get stuck? Do we complain? Do we panic? Not at all. We need to find a thermal insulation material. So do we have insulation? Yeah, we do have rigid insulation. Okay, so let's use rigid insulation. Rigid insulation is polystyrene. So let's use it. Rigid.
Is
Yep.
is glass wool the same as fiberglass insulation, or are those two different things?
Are there fiberglass here?
I don't know.
It's the same. Well, it's the same. Glass wool, rock wool, fiberglass. Yeah, they are the same family. It's not exactly the same, but of course, glass wool doesn't have anything to do with rigid insulation. The rigid insulation is foam. Fiberglass and glass wool, yeah, they are two. Yeah, they are alike. They are not exactly the same. But if there were fiberglass here, I would use that. But as long as I see, so we have this wood joist. No, this is not. So we don't have it. So what do we have? We have insulation. Can we create our own material? We can create our own material. Let's do this. So we start with the rigid insulation. Okay. So for the rigid insulation, if we click here, here you see that we have create and duplicate materials. So click here. So duplicate. Okay. So let's call this glass wool. Okay. So now we have glass wool. Is it that easy? The description, it's not rigid foam insulation board. This is glass wool, whatever. Okay. Glass. It's stone, ceramic, concrete, earth with generic leaking miscellaneous plastic stone system. Okay, generic. Don't go crazy. So this is the identity. Then we have graphics. This is the way it is represented. So we can select here the hatch. I don't know what is a good hatch for glass wool, something like that. Okay, no, this is wood. So anyway, I don't mind. The appearance, we are not talking about rendering options. So the appearance is how it's rendered in your rendering views. We are not worried about this in this course, but we are concerned about physical, especially the thermal properties. Okay, so here we have thermal conductivity, specific heat, density, porosity, reflectivity. So there are a lot of things here, but as far as we are concerned, we have to deal with thermal conductivity because this is what we are studying today. We are not studying specific heat or density or emissivity. That matters, but matters in other, we are not talking about these properties today. So let's change the thermal conductivity. So if we go to glass wool, what was the thermal glass wool? 0.231. Okay. So the thermal conductivity, oh, and that's why I have this column here. Units are very important. I don't think I think I'm too, I'm always talking about units and be careful with units and place units at the end of your results, whatever. So, but look at this. Here we have a thermal conductivity, and these units are BTU, inches, feet square, hour, Fahrenheit. But the units of this thermal conductivity are BTUs, hour, feet, Fahrenheit. Okay, so this is BTU inches, feet square, and this is BTU feet or foot. Why? Well, this is the crazy imperial system. With international systems, these things don't happen, so everything is easier. because we can either use the thickness in inches or we can either use the thickness in feet. If we are using the thickness in feet, we need these units. If we're using thickness in inches, we need these units. Okay, anyway, I have highlighted this yellow column because this is the thermal conductivity in Revit units. Okay, so if we want to place the thermal conductivity of this glass wool, this is not 0.23, it's 0.0193, 0.193. Okay, what's the difference? Basically, you have to divide this value by 12. So if you click here, so this is this value divided by 12. We get rid of these inches, and instead of square feet, we have feet here. Anyway, I've done this for you, but if you are changing, if you are creating your own material in Revit, and this is something that I recommend you do because by default, we don't have all these options in Revit. Okay, so if we are calculating these kind of things, we should be able to create our own material. And this is what we have done. So we didn't have glass wool. Okay, so we duplicate this material, we change the name and the description, and then we change the thermal conductivity. And we apply. We click OK. And now this is glass wool. But be careful because if we are doing this with Revit, we need this column, not this one. If we use this column, we are making a huge mistake and the result will be completely different. Okay. Anyway, we have created the thermal insulation, glass wool, and what was the thickness? It was 10 inches. So 10. And what's next? We have vapor barrier. Okay, so here we have a membrane layer. When we have a membrane layer, Revit recognizes that it doesn't have a thickness, so you don't use this. And when we are doing this, we can. Do we have a vapor? We have a vapor retarder. Okay, retarder, vapor barrier. We can use this one. Okay, so a vapor retarder, and don't change this because it's a membrane layer, so it doesn't have a thickness, or the thickness is so small that Revit, yeah, you don't need to include a thickness here. Then we have air. So this layer is again air category. Air. Okay, thickness, it's 2 inches here. And finally, we have a gypsum board. So, and this is the finish. So we have 2 finishes here. I think it's the same. So we can either use finish 1 or finish 2. Category, do we have gypsum? We do. Okay, we have gypsum board. And the thickness is 1 inch. No, 1 foot. 1 inch. Okay. So what is the beauty of this? That here we have calculated the thermal resistance of the wall. Okay. But look at this, the thermal resistance is 67. Why? Because in our tool, it was 51. If we edit the structure again, yeah, so the thermal resistance is 67. Well, because the other thermal conductivities, so if you click here, brick, and we see the thermal properties. What is the thermal conductivity? It's 0.3. What is the thermal conductivity of our brick? Brick is 0.2, 0.28. This is 0.31. This is 0.28. Does it mean that this is wrong and this is right? No, there are thousands or millions of different brick or brickworks on Earth. So some of them are 0.3, some of them are 0.28. You know what I mean? Don't go crazy with this. We have to make sure that we are above or we are close to this R50. In this case, we are above it, 67. Why? Because I don't know, the Revit the Revit database apparently is using better materials than this database. But again, I have summarized this because usually in brickwork, we have a range of values from 3 to 4 or from 2 to 5 or whatever. So I have decided a value here and Revit has decided a different value. So maybe I am in I have selected the low value of this range and Revit has selected the high value of that range. Okay, that's fine. So I'm not concerned. Anyway, if this thermal resistance is 67 and this thermal resistance is 51, if we want to get the same results, probably I can change the thermal insulation here, maybe 9 inches. If I change it to 9 inches, now this is 63. Okay, so I want to be close to 50. So what if I use 7 inches? Okay, so it's 54 now. Okay. So look at this, using only 7 inches of glass wool, I get the same thermal resistance as in this detail using 10 inches. Probably because the database of materials that we have here for gypsum, for brick, for air or whatever is different than the database that I'm using here. Does it matter? Well, it matters. Of course it matters. But you can either be on the safe side, so selecting the lowest value, you are on the safe side, or you can specify exactly, okay, I'm using brick in this building I'm designing, I'm using brick, and the thermal conductivity of that brick should be this, not this one, okay? And then you make sure that your materials, or the other way around, you have a list of materials the construction company has provided you with, and then, okay, so what is the thermal conductivity of the materials that we are going to use? And then you place those materials either in this website or in this Excel file or in Revit. Okay, but we can have different software. We select brick, and by using different software, we get different results. Why? Because the database of this software is different than the database of this software. Can we fix it? Yes, we can. In Revit, I told you how to fix this. So we can select this brick, and then we can go to the thermal, and we can change this, and we click OK, and we change that thermal conductivity. So we can make all these thermal conductivities the same as the thermal conductivities we're using here. I don't recommend you do that. Or we can just okay, if this is 51, this is 54, so that's fine. Okay, so now you know how to change the detail in Revit. You know even how to create a new material. Okay, so you select one, duplicate, and then change the thermal properties, the thermal conductivity of the material, and then you have a new one. Then you have a new material that it's not in Revit by default. And next time it will be here, the glass wool. Okay. So let's do it. Now, once we have this material, we have this basic wall here. R80, so that means that the, oh, I think this wall is R50. Okay, so let's rename this. It should be R50 because R80 is the roof. Okay. So now we have the R360, R80 basic wall. And now I can start wall, this one. There you go. If we look at the 3D view, we select all these. We attach it to level 12. Oh, by the way, so we do have level 0, level -1, level -4, and level 12. So we are going to do something from level 0 to level 12, okay? So we have this wall here. Now we need a roof. So for the roof, architecture roof, I have to duplicate this. So I edit type, duplicate, and this is arch 360 roof R80. Okay, we edit the structure, and now how many layers do we have on that roof? There was 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. What is the structure? So we have X. Okay, so the first one is finish. Do we have asphalt here? We do have asphalt shingle. Okay, we can use this. And this is 1 inch. The second one was concrete. Concrete is a structural element. So here I can select concrete, masonry units, cast in place. Masonry units is for walls, cast in place is for structural elements. And then we have lightweight. Lightweight is not a structural element, and precast, well, we can either use cast in place or precast. So let's use cast in place. I think it was 12 inches. Yep, 12 inches. Then we have glass wool. This is a thermal layer. Now we should have the glass wool here, the material. Yep. So glass wool, 17 inches. This is what we did here, 17 inches. The next one is the vapor barrier. So the next it's a membrane layer. We can use a vapor retarder. No thickness here. Then air. Air. What is the thickness here? 3 inches. And finally, there is a finish, a gypsum. And it's 1 inch. Okay, so now the thermal resistance is 92. And in our, it was 82. Yeah, so again, the materials have different properties. So if we want to make this, let's say 1 foot and 2 inches, click OK. Now it's 79. No, slightly more, say 1 and 3 inches. Okay, now the thermal resistance is 84 and this thermal resistance is 82. So yeah, they are in their 80s.
Fernando, can you go back
Yep.
to the list of materials?
The Revit list.
Yeah, for the roof.
You want to look at it or do you want me to explain anything else?
I just need to look at it. I missed a couple things.
Okay, so I will go over it. Indoor, this is okay. I'm going to edit this. So this is indoor and this is outdoor. Okay, so indoor we have a finish gypsum board 1 inch, thermal air layer air 3 inches, this vapor retarder, no thickness here, glass wool 1 foot and 3 inches, or this is 15 inches, doesn't matter. Then the structural element, concrete cast in place, 1 foot, and the asphalt shingles, 1 inch. Asphalt shingles. Okay, asphalt shingles are things like this. We don't have an inch, so it's much thinner. But anyway, so I have decided that an inch. But those are the asphalt shingles, and so it's not as thick as 1 inch. Doesn't matter. Okay, Zach, do you need anything else, or are you done with this?
I got it.
Okay. So apply, okay. And now we have this basic roof, arch 360 roof, R80. And we just do this. It has to be on level 12, the roof. And it goes from that corner to that corner. We don't want slope. So select the roof. Do not define slope. We want a flat roof. And we click, OK. And there you go. We have a masterpiece here, a box, okay, with roofs and walls without any windows. The good thing in Revit is that you can click here, and now this roof, it's something that so this is the roof, and here you have all the information. If you want to know the thermal resistance, you edit the type, and you get the thermal resistance here. If you want to know the area, here you have the area. It's 1921 square feet. The volume, the thickness, the everything. Well, just this. If you want this wall, you have the area of that wall here, 360. And if you want the thermal resistance, you edit type, and it's 54. Okay, so you have these elements, and now you can see all the properties of this element. We don't have a floor, so let's create a floor, and let's create an architectural floor, and let's do this generate one. Okay, so we're not going to change the floor materials. There you go, and click OK, and we do have the floor here, and I wanted this floor to go from level 0 to level -1. Okay, so we have a 1 foot floor slab without any thermal insulation. We do have thermal insulations here and there. If you go to level 0, I don't know, but depending on the level of detail, if you don't have any detail level, you see just 2 lines. But if you increase the fine detail level, here you have the thing. So remember that we created this glass wool with this ugly hatch. And then this is the, oh, so that's interesting. Look at this. I think this is the gypsum board. This is the air cavity. This is the glass wool. We have another air cavity, and this is the brick. Because if we go to edit type, cancel, we select the wall, edit type, and see the brick. Okay, so the pattern is this diagonal thing here. Okay. So that's another thing that we have to make sure when we are creating walls. Now the brick is inside. It's not relevant, but we should change this. So if I press the space bar, I change the orientation of the wall. Okay, so I have to do this because I want the brick to be outside, all of them. Space bar, and I change the orientation. Okay, so you need to be aware of, if you are not aware of hatches, we have this realistic, so we have the, now we make sure that the brick is outdoors. Okay. And to see what we have done on the roof, I think we need a section. So let's create a section here. And let's look at section 1. Okay, so here we don't have any information. We have the details, and I think it's fine because this is the thermal insulation, this is a concrete, this is the asphalt. So I think the order is correct here. We have a mess. Okay, so this is not well, in visual representation, we are dealing with these details now. So if you are taking this course now, I will show you how to fix this transition, this wall to roof transition. If you have already taken this, you should know how to fix this, how to create a nice call out here and to connect these things properly, okay? But anyway, it's not relevant. And what about the floor? The floor, we haven't selected any material for the floor, so it's just a slab. So we can carry out the first analysis, the first energy analysis in Revit. What do we need? First, we need to specify materials. And we have the materials here, and we have the thermal resistance of the walls and roofs. We should do the same with the floor, but we're not doing that, and I'll show you why now. And now we can click here on this Analyze tab. Okay, I told you that if you have installed the Insight plugin, you should have these two elements, the lighting and the solar, but we are not using this so far. Okay, so in Revit, you should be having this space information with zone, and then these heating and cooling loads. Okay, so the Analyze tab, and here you have a heating and cooling loads, but that is connected to spaces. So first we need to create a space. So we do this in the plan view. Okay, so here you have to click space, and if you see, if we are outdoors, we create a space here, but this is not acceptable. Okay, so we have to be indoors so that we create a space. On this template, the space is highlighted in green, but by default, we don't have this. How can we change that? It's in visibility graphics. First, spaces are in mechanical discipline. So if you select mechanical, you have spaces here. Where is it? Spaces. And then you have to make sure that everything is color field, interior, and reference. Everything is selected here. Okay, because if it's not, when you apply, you don't see the space. It's, well, it's there. So if you hover the mouse, the space is there, but you don't see But since we're working with heating loads and all that stuff, we should be looking at the space to realize if everything goes well. Because look at this, the space fits the walls, it's perfect. But if we look at the section, well, first here, we don't see the space. So we have to go to visibility graphics, spaces, click on everything. And now we see this. And as you can see, the space is not up to the roof level. Okay, why? Well, this is what Revit does by default. And if you click here, let's do this. This is not correct, but I want to show you what happens if it's not correct. So if you click here, heating and cooling loads, if you analyze this, the first thing is that if you don't have spaces, you can't use this tool. Okay, so you need spaces. So since this is a very basic building, so we have only a space here, that's fine. Here we have location, Boston, Massachusetts, the building type. We can change this, but it doesn't matter. I want you to click on details. So by clicking here on details, we see that there's a warning. So when we see this element, we see that there is a warning. When we have a warning in that space, that means that something like this is happening. Okay, so doesn't fit with the shape of the room. Okay, so we have a room here and the space is not well. Yeah, so in this case, it can be a problem with the plan view or it can be a problem with the section. Usually it's with the section. So we can select the space and here we have information. So first thing, we have to rename spaces because there will be space 1, space 2, space 3. If you have a complicated building with 100 spaces, you don't know where you are. So again, giving names, it's the most difficult things on earth. So we have to make up our mind. What is this space? I don't know. We need a criteria. It's I don't know. It's 1 first floor. I don't know. It can be classroom 1 or whatever. I don't know. Let's say office 1. Okay. If this is an office building, we have different floors. So this is the first floor, office 1. Okay. I'm not good at giving names to things, by the way. So we have this, and now we have to fix. We have to. This is the upper limit. The base offset is this, so the level is level 0. So the upper limit should be level 12, and no offset 0. Okay. So now the space fits perfectly here. So if we go to the heating and cooling loads, if we go to details, there is no warning. And this is the name of the space, is office 1, first floor, office 1. Okay. So before starting placing spaces, blah, 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 make sure that, because this is very important, we have to be accurate. So take your time. Once the model is done, if you want to carry out the energy model, make sure that you place all the spaces. Make sure that all spaces are fitting the walls and the roofs. Okay, so take your time before analyzing anything, because it's if you don't take your time and you have mistakes in spaces, or you don't know the name of the spaces that you are dealing with, there will be a lot of warnings and it will be a mess. Okay, so make sure that when you click details, we don't have any warning here. So when we're done with this, we can calculate. And we have a nice report. So on this report, we have the project name, the address, we don't have it, whatever, but building summary. We have the building type is an office building, the area, the floor area, the volume of the building, the peak cooling load, the peak heating load. The problem with this is that we have made a lot of decisions. You are not aware of the decisions that we have made, But when we analyze this heating and cooling load option, okay, in general, we have new construction. You have selected the HVAC system, and in details, you have selected the heating information, the cooling information, the outdoor air information, and if you select the space, we have all this area, the lighting. Okay, so we have made a lot of decisions. We have here values by default. It doesn't mean that they are the correct values. Okay, so we will work on that. But what do I want to analyze now? Here we have a space summary, and this is our space. What do we want? We want the heating load, and we want the cooling load. Okay, so far we are calculating heating loads. So the heating load of that space is 3,700 BTU hours. But here we have ventilation, we have lighting, we have a lot of things. So we have to go in this summary component by component. So here we have walls, we have we don't have any windows, we don't have any doors, okay, because it's just a box. And here we have the roof. So if you analyze this, we don't have doors, we don't have windows, we don't have skylights, we don't have partitions, we don't have infiltration. So we can compare the total BTU through the walls. Here we have the wall area. Okay, so we can use this now to by the way, reports are here. Okay, so in this project browser, you have the plans, elevations, and you have reports. Okay, so this is the load report 1. This is the one that I did to prepare the class, so I'm going to delete it. This is the loads report number 2, and it's here. So you don't lose it. Even if you close this tab, you say, where's my report? It's always here. Okay. So I want to compare these two. So I have to compare this because this is the wall cooling load. So it should be 1,186. And but I need the wall area. Okay, so the wall area is 2,160. So I can type here the wall area 2,160. What is the roof area? The roof area is 1,800. So the roof area is 1,800. So if we go all the way down here, you can find the thermal load. Now here, we can find the thermal load through walls. Okay, so my thermal load is 3,300 and something. Revit through walls is 100. And why? Well, there's something that we have done. There's something wrong with it. Okay, if this is 1,180 and the other one is 2,100 and no 1,200, that's fine. But here this is 1,100 and this is 3,300. So there's something wrong in this wall area. Maybe the wall area is not correct, or the R value is not correct, but we have to find out. Okay, but that's how we compare two things, because look at this. I think I have done the same. Okay, so I have the same wall here, the same R value. I think I have the same area, but the results are completely different. So oh, but this is the cooling. Okay, so the heating, sorry, it was the heating load is 2000. And my heating load is 3000. Why? I know why, but do you have any idea? No ideas? Do you think I have made a mistake with the wall area? Hello, are you still there?
Yeah.
Yeah, but do you think I have made a mistake with the wall area? The wall area is 2160. The wall area is 200, 160. Okay. The R value, is it the R value different? This is 51. And what is the R value of my wall? If I select this, edit type, yeah, this is 54. But does it explain the difference? Does it explain that the heating, because we are looking at the heating load through the wall, is 2400 and this is 3300? Well, what is the explanation? What is the outdoor temperature? Look at this. Winter dry bulb is 8 Fahrenheit here. And what have I used? I have used -10. So this should be, if we want to compare this, it should be 8. Okay, so now this is 2600, and in Revit is 24, almost 2500. So that makes sense. Okay, so it's not 100% accurate, but the order of magnitude. So if it's 2000, this, my Excel file should be 2000. It can be 2400, 2600, but it's not like 2000 in Revit and 4000 in my Excel file. So now I can rely on both tools, because by having the same indoor temperature, the same outdoor temperature, the same wall, the same area, results are alike. What about the roof? So for the roof, in my case, this is 1300. In Revit, the roof is 1300, almost perfect. Okay. Well, we are run out of time. See you on Wednesday. You don't have to do anything.